Good evening, everybody. Welcome to the AWS Portsmouth user group. Thanks for joining us. Tonight, we have a fantastic guest. We're very excited. Mr. Jeremy Daly, AWS Serverless Hero, is here to talk about how to fail with serverless. Before we get into that, though, a couple of show notes. If you want to get in on the conversation, join us at AWS. If you at AWS on Twitter, you'll see us, and we can answer questions there. We also have our website, awspub.org. You can meet up with us on Meetup, and you can Slack us on Slack. If you are in the room with us tonight, you can do live Q&A with us, and we highly encourage it. But if you are not talking, please mute your microphone so that we don't get any bleed on the sound. Tonight, like I said, we've got Jeremy Daly. He's going to talk to us about serverless. And he is exactly the right person to talk to us about serverless because he is an AWS Serverless Hero. You can catch up with his bio at jeremydaly.com. You can see his serverless credentials over here, and here's a wonderful picture of him on Twitter. So with that, let me stop sharing and allow you to pick it up, sir. The power is yours.
Let's see if this will work. All right, I'm going to share the PowerPoint. All right, can you see the
yes, we can see your screen.
Presentation there. Perfect. Okay, well, thank you, first of all, for having me here. I would love to have been there in person. I'm just down in Massachusetts, so Portsmouth is not that far from me. So maybe some other time when the world goes back to semi-normal, we can all be together again.
That would be wonderful.
So I usually do these. I mean, we've got a small group of people, so if anybody has any questions, feel free to jump in and ask questions, and hopefully you can take some time and answer those. It'd be a little more interactive than just kind of talking to you all for 45 minutes or so. But anyways, so let's see if I can actually advance the slide here. There we go. So that's me. I'm a CTO or the CTO at a small company out of New York called AlertMe. I do a lot of consulting with companies in the cloud. I've been doing this for a very, very long time. The picture doesn't quite show all the gray that's actually in my beard. Plus, I have a 12-year-old and a 14-year-old daughter, so that is contributing to the gray as well. I started working with AWS very early on. So around 2009, I started doing stuff with EC2 instances, servers, and did that for quite some time until Lambda came out in GA around 2015. I started playing around with that. I do quite a bit of speaking. I have a number of open source projects. My blog is at jeremydaly.com. I have my newsletter that I do every week that just consolidates or aggregates a bunch of links on serverless, and I opine on them and try to give some insight into what's happening in the space. And then my Serverless Chats podcast, which is now a video podcast. So if you like to stare at people talking, then this could be for you. And also I'm a serverless hero, as we mentioned. So tonight I want to go through a bunch of different things. It's going to get kind of technical, but it's more so to give you an overview of just kind of what's possible and kind of get you thinking about some of these things. So we'll talk about distributed systems and serverless. We'll talk about writing code for the cloud, which is different than writing code just for a regular server. We'll talk about the failure modes in the cloud, which is where the how to fail with serverless sort of comes in here. We'll talk about a couple of different serverless patterns that we can use to deal with failures in the cloud, and then we'll go over decoupling our services and why that's important for building resilient systems. So a couple words on distributed systems. I think we're probably familiar with these, but they're basically any system that uses multiple systems. They're connected with a network. They have to pass messages back and forth to one another. They need a way to communicate their actions. They're also really, really hard to build. So if you've ever worked on a distributed system, you know this. If you've worked on a distributed system and you say they're not hard, then you are really, really smart, because these are very difficult things to work with. If you're familiar with this man, Werner Vogels, he has a famous saying that everything fails all the time. And this is something where, especially people new to the cloud or new to serverless that maybe are just sort of working in monolithic applications or things like that, they don't quite understand, or there's this thing called the 8 fallacies of distributed computing. And this is something that many people that are getting into distributed computing or even cloud computing, they don't quite understand how this works. But these are these different fallacies here, and I'll just go through them quickly. So the network, we know, is not reliable, right? We have packets lost all the time. Things can't connect. Things need to be rerouted. Obviously, you're routing over networks, so latency is never zero. You are going to run into bandwidth limitations. The network is only as secure as as you think it might be, but there are certainly ways that people can jump on and send messages into your network that might not be trustworthy. So you have to think about that. The topology is constantly changing, especially in systems that are bouncing you back and forth between 3 different availability zones or however many different regions across the world. There's multiple people with their fingers in the pot here. It costs money to transport data, obviously, and the network is different. So you may be hitting different versions of systems, different, different types of routing, all kinds of things that could be different. So the thing that we need to think about when we start building serverless applications is the fact that these are essentially distributed systems, but they're sort of distributed systems on steroids. And the reason for that is that they're much smaller, right? So if you think about even containers, you still have monolithic applications or distributed monoliths that are running in sort of these enclosed compute units. You're starting to break this up even more when you start going to serverless because you're using functions to do this, and you're using third-party services and managed services that really break them down. Serverless functions are obviously stateless, or I don't know if I should say obviously, but they are stateless. So in order for you to do any sort of connections or any sort of rehydrating of data, they do require a network access. So if you want to rehydrate state and things like that. They're highly uncoordinated, right? You wouldn't think this, but they are. So in order for you to have 2 functions communicate with one another, or 2 different processes communicate with one another, you need to use queues or something like PubSub, or you need a event bus, or maybe you need to use a state machine. And they're also they're heavily reliant on other network cloud services, right? So you're not installing a MySQL server on a Lambda function, you're using RDS, and you're not building your own queues, you're using SQS and things like that. So it also requires you to be very familiar with some of these other services. So what does it mean to be serverless, right? This is a user group for AWS, but I'm sure you're probably familiar with sort of the company line here from AWS, which is there's no server management, there's flexible scaling, you only pay for value. It used to be never paid for idle. Now, they charge you for things even if you're not using them. And then this idea of automated high availability. What you probably don't know if you haven't played around with serverless is that it is a lot of configuration, and you need to have a really deep knowledge of all these different cloud services that you're using. And it's also highly event driven. So this is a new way of thinking for a lot of people. We're not communicating synchronously in most cases. We're passing data, in some way that's getting buffered and then eventually making it to a destination. And you don't have that sort of direct response there. So it's a different way of thinking for a lot of different types of applications, especially when people are used to things like sharing state and sticky sessions and those sort of things that are just not part of the serverless ecosystem. So there are a lot of different services in AWS that you have to communicate with. They kind of classify some of these as serverless, things like DynamoDB, SQS, SNS, things like the Comprehend or any of the media services they have. And then they also have sort of this classification of things that they consider to be managed. So whether that's Elasticsearch or Elasticache or RDS. And these are great because they do most of the managing for you, but you still have to worry about the size and sort of the provisioning, the capacity provisioning, things like that. And then finally, you have all these things that are non-serverless. So anything running on EC2, Kubernetes, and Docker, and all that kind of stuff is just definitely not serverless. But you do have a lot of services that you have to think about communicating with. So the way we used to think about building applications.
Привет, это Навальный.
I'm sorry, what?
Hi, if anybody can mute their mic while unless you have a question, thanks.
Okay. So anyways, so a lot of the ways that we used to think about building systems was along these lines of reliability or high availability, where we would say, we want to get as many nines as possible. We want this server to be running for as long as possible. And this was sort of this way of maintaining uptime or operational performance. But we don't really have to think about keeping things up and running anymore with serverless, especially Lambda functions that run for a very short amount of time and then shut back down. And we don't have to worry about maintaining the availability of an SQS queue because somebody else is managing that for us. So that gives us an opportunity to focus on resiliency. And what resiliency is that's the ability for you to absorb failures and then still provide some sort of acceptable level of service. So it's not about preventing failure, it's about understanding ways in which you can gracefully deal with this. And so this is something that's very popular. You should definitely look into if you're not familiar with things that Netflix does, sort of graceful degradation, things like that. I had an episode recently on serverless chats with Adrian Hornsby. We talked a lot about resiliency and global resiliency. That should give you a really good overview of what this is about. But I want to get into this idea of writing code for the cloud. So typically what we would do, any type of code we would write in a serverless application, unless it's something like VTL and configuration files, we're going to be using Lambda to do our business logic. And Lambda is an ephemeral compute service, which means that it's going to spin up and it's going to spin down. It runs in response to events, so it's not just sitting there waiting for things to process. There are a lot of benefits, though. It automatically manages the runtime for you. It'll scale up as much as you need it to scale up based on some limits that you can set. It uses a single concurrency model. So this is something that can trip people up, especially if you're using global variables and things like that, where you don't have to worry about sort of overlapping state and sharing state too much between invocations. But then again, there's no sticky sessions or guaranteed lifespan. So just something to think about. It's a very powerful service, but it operates very differently than something that would sort of be sitting there waiting for something, waiting for an API call, for example. So when we build traditional error handling systems and we think about retries, let's say I stand up an EC2 instance, I'm running Node or PHP or something like that, I would probably do something like this. I'd put a try catch statement in. So a request comes in, something fails, I catch it, I can do some logging, I can do some error handling, and then maybe depending on my rules, I say, well, I want to retry that operation. Serverless obviously has some challenges when it comes to this, because what happens to the original event, right? So let's say that you hit a try, you have a try catch block, you get an error, your catch block fires, and you want to record that original event. So that would be one way you could do it, record that original event so you have it, and now you haven't lost it, but it's buried in log somewhere. But what happens if there's a network issue? So a lot of people think that it just writes directly to CloudWatch. Lambda functions don't write directly to CloudWatch. There's actually a telemetry service that runs within Firecracker that eventually hands the data off to CloudWatch. So it is very possible that that can fail. And if that fails, the data never actually makes it to CloudWatch. What happens if that container itself crashes? So if the Firecracker container that's running your Lambda function, if that crashes, that can never even connect to a logging service, but it also can't run code in order for it to reprocess the error, for example. And then what happens if the function just never runs? So it's entirely possible that a request comes in and it gets buffered because there's a concurrency limit set and it can't run. And so the event never runs, maybe it never gets the resources it needs, and then that event is just completely lost. And I think we all would agree that losing events is a very, very bad thing. So we have to think about the ways in which our functions can fail, the types of errors that we're going to get, to understand how we can deal with all these different failures. So you obviously have the unhandled exception. That's just something that happens. It couldn't connect to the database, or something failed, or whatever happened. And that would sort of be your traditional error that maybe we could put in a try catch. But then you have things like function timeouts. So if you have a 30-second function timeout set and you have some long-running function and that dies, your retry code, your error logging, all that stuff never happens, and you lose all that information. You have out-of-memory errors. You can get up to 3 gigs of memory, but let's say that exceeds, it's going to throw an error. Your retry logic would never fire. You also get those throttling errors that I talked about, where you have your concurrency set to 50, and then that 51 or 51st concurrent connection comes in, and that doesn't execute, that gets kicked back, and that event is lost. So a couple of things that I try to think about is that the cloud is better than you at things like error handling. It's better than you at retrying failures, at understanding network failures, at understanding its own network topology. That's one thing that you have no insight into in terms of how AWS routes things internally. And then that gives them a lot of capabilities when it comes to handling failover and redundancy. So the question is if the cloud is better than you at doing these things, then why not just let it do those things for you? And the way that we do this is by what I call failing up the stack. And essentially what you want to do is you don't want to swallow errors with a try catch. It's common that you do a try catch and then you try to do something within that error, but you then return a 200 that process still was successful. If you do that, then the cloud can't use your error, or it doesn't know that the function failed, and it will just assume that everything was okay. So you want to fail the function. There is a caveat here. Sometimes you don't want to do this, but most of the time you do. So you want to make sure that when that function fails, that the errors that it generates, those get returned directly to the invoking service. And we'll talk about why this is important in a few minutes. And then you want to make sure you configure all of these built-in retry mechanisms that will automatically reprocess those events based off of certain criteria. And then you want to make sure that you utilize dead letter queues, which we will talk about more in a minute, in order to capture those failed events so that you don't lose those events. So in order to get to the point where we understand how we can deal with failures in these, in these Lambda functions that have this business logic in it, we have to understand these different types of Lambda functions. And I tend to classify them into 3 different types. So there's the Lambda-lith, and we'll go into detail with all of these. This one is a good onboard, but it's kind of scary in terms of how we can deal with failure. There's the fat Lambda, which is a useful pattern that you can use depending on what your use case, but really try to, that we should try to use. So let's talk about the mighty Lambda-lith first. So this is the updated version of the monolith. This is the Lambda version of it. And this is essentially when you take your entire application and you stick it into one single Lambda function. So you just take your Express app or your Flask app or any of those things, and you just lift it and shift it and put it into a Lambda function. This works really well, and it works for most people. The events to these things are typically synchronous, so you're usually connecting via API gateway or something like an application load balancer. But the problem is that any partial failures of this have to be handled in the code, meaning that we have to write those try catches, because if that fails somewhere, you can't retry it the same way that you would if it was asynchronous, which we'll get into in a minute. Then there is the fat Lambda, and this is essentially when you take multiple related methods and you co-locate them into a single Lambda function. So this is often used if we are trying to optimize some sort of a synchronous operation. So you might see this in a checkout, for example, where it has to connect to maybe multiple APIs, and that all has to happen in real time in order for certain things to work correctly. And it has been used. I know that Lego uses something like this. I know that that Bustle uses something like this. So it's certainly a valid pattern. Partial failures are still handled in the code, though, so you want to use these limited in limited circumstances, but under the right circumstances, this can actually be really, really useful. All right, so let's get to the single purpose Lambda function. This is where I think we should all try to strive for. And this is essentially where you have a very tightly scoped function, handles all of that business logic, a very single discrete piece of business logic in one function. You can invoke these either synchronously or asynchronously, because the returns from these should be compatible or useful in either way. You're only executing one piece of logic, so whether you call them synchronously or asynchronously doesn't matter. The failures are total failures. So this is great, because if I try to insert a record into the database, and that's the only thing that function does, if that fails, then I can pass that failure back to that invoking service, which there's a bunch of different ways we can do that. And then I can use that to either retry it or figure out what my retry policy is going to be. And that's much more sustainable than having it just return because it failed somewhere in the code, where it tried to write to the database and then it needed to update something and then it needed to send an email. We don't know how far it got in there, and it's very difficult for the cloud to manage that if we're not passing the information back up. And the other great thing about building these as single purpose functions is they can be reused, right? So you can take each one of these functions and throw it into a number of different workflows, which is great. You can use them in step functions. You can use them as part of Lambda destinations. We'll talk about some of this stuff in a minute. But they can scale, or they can be throttled independently. And then also you can set the permissions for those, the IAM permissions, very tightly scoped, so you can focus on that principle of least privilege. If a function only is inserting data into a DynamoDB table, for example, then that's the only thing that that function can do. If that ever gets compromised because of maybe a third-party service or some other bug is introduced, then you don't end up scanning the table or exposing some other data that way. All right, so let's get into failure modes in the cloud. This is a lot of overly technical content ahead. Again, this is the kind of thing where all of this stuff that I'm going to tell you is in the documentation, but it's sort of buried and you got to look for it in different ways. And what I like to do with this presentation is just give people an overview so that they understand that these things exist. You don't have to take away, everything from it other than to know that the failure modes are different depending on the circumstances. And then you can go look these up, look these up in the documentation to figure these out. So before we get into anything to do with the failure modes themselves, we do need to talk about retries. So in a distributed system, retries are very vital. If you tried to connect to service B from service A and that failed, and then you never retried it, that is going to fail maybe 1 out of 1,000 times because of a network issue. And so those need to retry. So it has to be able to retry these different things. Otherwise, otherwise your failure rate or your failure rate would be very, very high, and your system wouldn't work very well. So most of the cloud services, specifically the ones for AWS, they guarantee what's called at least once delivery. And that sounds great, except that it is possible for the same event to be received more than once. So it's possible that it goes to send the event, your service accepts it, but for some reason the invoking service doesn't realize that it was sent successfully, so it retries it, and then your Lambda function, for example, gets called twice. That can be pretty bad if you are, say, maybe charging someone's credit card multiple times or certain things. So you need to make sure that when you are retrying operations or any operations that might be retried in a distributed system, you want them to be idempotent. If you're not familiar with what idempotency means, it's essentially the ability to repeat an event multiple times and get the same result. So it's to minimize those side effects or to get no side effects. So if you think about something like updating a database record, I can send the same update parameters to a database, and other than maybe the modified date, for example, I'm always going to get the same result, right? If I authenticate a user, I should be able to authenticate a user, as many times as I want to. Maybe I get a different key, but for the most part, I haven't changed any other state in the system. And then if I was, say, checking to see if a database record existed, if it didn't exist, then I create it. If it does exist, I don't do anything. So I can try that same event 100 times, and it will only create one record in the database. So there are a lot of strategies to ensure idempotency. It is a major pain in some cases. It doesn't happen very often when events get retried more than once, but it does happen, and it's just something that something you want to think about. All right, so then dead letter queues. If you're not familiar with dead letter queues, they are a way to capture any failed process or any message that has failed to process or was skipped. And the skipped piece is important because it's not just about failures. There's other reasons why messages can end up in dead letter queues. These are great because, one, they capture the event itself, but you can also use them to do alarms. You can replay them. There's the ways you can go in, obviously, and inspect them and see what exactly the message itself was. And then depending on which service you're connecting these to, you can add these to SQS queues, SNS, Lambda functions. There's more services that these are being added to. I skipped over that, sorry. So these are important because they do allow you to take failures and make sure you capture those before before it calls that individual service. So if that service doesn't invoke, we talked about some of those reasons why your try catches might not work. These are where dead letter queues come in and can capture that data ahead of time. All right, so there are a couple different types of Lambda function or Lambda invocation types. We're very familiar with synchronous. This is the request response model. This is I make a call to an API, that API returns data to me. But there's also asynchronous, which is essentially the set it and forget it. That's when I send a request somewhere and it says, okay, I've captured your request and I will process it later. And then you have stream-based. This is where data is pushed to Lambda functions from something like a Kinesis stream. And then you have the pull-based or the polar-based, where you have a service that actually pulls data or pulls a service like SQS and will send that data into the Lambda function. So synchronous Lambda retry behavior is different than all the other ones. And so this sort of the important thing to remember here is that depending on how you invoke a Lambda function, the retry behavior is going to be different. So functions are invoked directly using that request response model that we talked about. When a function fails, it returns directly to the invoker, which means that the retries are delegated to the invoking application. So most of the services some of the services will automatically retry. So if you're using, and I'm going to put the mute on my Alexa here so it doesn't respond to me. If you have an Alexa skill, for example, and I did this last time I was giving this presentation and it started talking to me. If you invoke an Alexa skill, it'll try to call, the Alexa service will try to call your Lambda function synchronously. If that fails, it actually retries it a couple of times before it will spit that back. And then also like Cognito, for example. So if you're using Cognito to do a custom authorizer, it'll call your Lambda function. If that fails, it'll try it a couple of times. But pretty much all other services don't retry. So API gateway, application load balancers, and step functions, those actually kick the data back, or I should say, they will not automatically retry. You have to build those retries in yourself with those individual services. And then API Gateway and ALB, for example, you actually get the raw error can go right back to the client. So the client itself would actually be responsible for the retry, whereas step functions, you can build some of that in there. All right, so asynchronous Lambda retry, again, different than synchronous. So there is actually a Lambda service that sits in front of Lambda functions. And what happens is when you make a request to a Lambda function asynchronously using the event response type, then essentially what that does is it puts it into a queue, and it's just behind the scenes, it's an SQS queue. And then if it accepts that message into the queue, it will send you back a message, a 202 status code, and it will disconnect. So now that function or that event is sitting in a queue somewhere that you have absolutely no visibility into. And your calling service, your invoking service, will just assume that it was received correctly. Then what happens is the Lambda service will attempt to process your function. It'll try to call the actual Lambda function. If that fails, it will try it up to 2 times. You can configure that with the max retries attempts. And then you can also, if it gets throttled, you actually have a built-in throttling mechanism in there where that queue will actually retry for up to 6 hours, depending on what you set your maximum event age in seconds to. And that's actually really cool because you don't have to worry about the queue. You don't have to think about that. But there are reasons why this, again, could potentially fail. And so when events fail more than those 2 times, or they expire because they can't get, they keep getting throttled, they eventually don't make their way, or they eventually don't get invoked, those can get sent to either the dead letter queue that we talked before, or an on failure destination, which we'll talk about, but is very much so like a dead letter queue, just with a few more features. Okay, so stream-based Lambda retries. This is where records are actually pushed to a Lambda function. They are pushed synchronously, so the Lambda function behaves in a synchronous manner, meaning that the system that pushes the data is handling the retries there. So Kinesis or DynamoDB streams can get sent in large batches. You do have a setting called the maximum retry attempts, which defaults to 10,000. And this means that if a batch of 1,000 records, for example, gets pushed to a Lambda function and that fails, if you let the default stay at 10,000, it will retry that Lambda function 10,000 times. I actually had this happen to me one time because it was an experimental thing, and then I realized that's really bad. So think about the maximum retry attempts. That's something you do not want to just leave at the default. There's also a maximum record age in seconds. So if a record isn't processed, it can stay there for 7 days. Now, these are ordered, so this is also a blocking mechanism, right? So if you get an error, it'll just keep failing and no new records will be processed. They'll just keep backing up and backing up. There is a very cool feature that they added I think it was last reInvent, called bisect batch on function error. Super easy. It's just a checkbox that you turn on. And what this does is, let's say you have a batch of 1,000 records that gets pushed into Lambda, and that batch of 1,000 or of 100 fails. Then the service will automatically split it into 2 batches, 50 and 50, and then send both of those batches in, assuming that there's a poison pill in just one of those. Then one batch of those will process correctly. The other batch will fail. It'll split it 25, 25, retry those 2, and so forth. So it'll keep splitting that and eventually find where that poison pill is. Once it isolates it down to a single poison pill, then it will go ahead and push that into your on failure destination. So either the record gets skipped because the maximum retry attempts were exceeded, or the maximum record age in seconds was exceeded, or it was detected from as a poison pill. Then it will get pushed to one of these on failure destinations, which you can set as either a SQS queue or an SNS topic. All right, so polar-based Lambda retry behavior. So the Lambda polar is another service that exists that will pull records synchronously from SQS. This is in batches of 10. There is no bisecting here, so unfortunately, if there's an error, the entire batch fails. You have a maximum receive count setting, which is similar to that maximum retry attempts on the stream-based, where if the message is returned to the queue this number of times because it keeps on failing, then it will get sent to that DLQ. The polling frequency here is tied to the concurrency. This is one of the things that kind of confuses people. You can't set your concurrency to like 5. You kind of can, but you need to set your concurrency to something reasonable, maybe 10. And then there's things like visibility timeout and some of these other things you have to configure in order to get that to work correctly so that you don't have records being returned back to the queue multiple times, triggering a retry policy that will throw them into that DL queue. So it's well documented. You need to look it up. But if you are doing a Lambda polling and you find that messages that shouldn't be failing are going into your DL queue, it's probably because your visibility timeout isn't set correctly, and you need to find the right settings for those and tweak those correctly. So we mentioned Lambda destinations. So a couple things about these. These only work on asynchronous invocations. So if you have a synchronous invocation from API Gateway, for example, and it fails or something like that, that isn't going to work with DL queues and it's not going to work with Lambda destinations. But if you do invoke it asynchronously, then you can actually send the response from that based on whether it's successful or it fails, or actually you can do both. So you can have a success route or a success destination and a failure destination. If you are building new systems, then you should favor on failure over the standard DLQ. They're essentially the same thing, except that DLQs only support SQS and SNS, and it also, those two, or the DLQ only supports the original message itself. So there's no context around that. Whereas with on failure, those will actually send the context of the message. You'll get things like the stack trace and some of that other stuff. The other thing that's great about destinations is you can send them to SQS or SNS, but you can also trigger another Lambda function off of them or event bridge. So depending on what your use case is, I tend to favor sending success messages to event bridge, because then I can use that as a trigger to say that some process finished correctly, and then usually use SQS queues as the failure. But if you did want to launch another Lambda function directly, or you wanted to trigger an SNS topic that maybe sent it to an SQS queue in somewhere else, you can do that. It's very flexible with Lambda destinations. And like I said, you get much more context with these. They are destination specific. So if you send to SQS or SNS, it's just going to come through as the message. So you'll get the original data plus all that context information if it is if it's a failure. If you send it to a Lambda function, then that's just straight pass as the payload. And then Event Bridge uses it puts the data in the detail. It also has the source set as Lambda, which is strange because everything else from Lambda has a capital L, but this has a lowercase l, so it's something to be aware of when you're writing rules. And then also you get the information about the detail type, whether it's success or a failure. And then you also get those destination ARNs as well as the function ARN. So you get a lot of information in there that you can actually make some really good decisions on about how you want to handle those when they come into Event Bridge. You get a lot of power with those rules. So we mentioned this SQS redrive policy. When a SQS message gets returned multiple times, then it can only support SQS as another DLQ. So essentially, if you have a queue that's storing a bunch of data and that fails a number of times, you can't send it to like SNS, for example. You have to send it back to SQS to a different queue. So that's based on the number of maximum receives that is set, and if that gets exceeded. And then also you have SNS redrive policies. These are attached to subscriptions, not topics. So this is kind of confusing. I'm not sure what the use case is here. If you were, say, like sending them to emails or something like that, or if you had 10,000, APNs or 100,000 APNs that you're pushing into, you wouldn't set a DLQ on every single one of those. So these really only come into play if you're using something like, maybe invoking a Lambda function with it, or maybe sending it to SQS or something like that, where you might want to have these redrive policies enabled. You can only use SQS as these, so you can't send a dead letter queue to another SNS topic. And then certain times this doesn't apply. So like if a Lambda function doesn't exist when you try to invoke it, then it wouldn't try to retry that. The cool thing about SNS to SQS, if you've ever used this, is that it does have an insane number of retries. So it's almost guaranteed. So any message that goes from SNS to SQS or to Lambda will actually get retried over 100,000 times through 23 days. So I always joke that even if the zombie apocalypse comes, your messages will still be being delivered from SNS to SQS. So that's something you can, you don't have to worry about. So messages can also go to other things like SMTP, SMS, and mobile. They have a completely different retry policy. Don't know why, but they retry 50 times over 6 hours. And then HTTP endpoints actually have a whole customer-defined thing that you can put in. So you can configure how many retries, the delay, the back-off strategy, whether it's linear or exponential, and things like that. And then finally, Event Bridge has some retry behavior, which is pretty simple. It just keeps trying to deliver it for 24 hours with some sort of back off. I know they're working on ways to make these things a little bit different or a little bit more flexible, but failed events are essentially lost, although this is very unlikely because most of the destinations for your Event Bridge rules are going to be other AWS services, and the likelihood of, say, SQS being down for 24 hours is very, very unlikely. And then once the events themselves are actually accepted, then the failure modes of all those individual services kicked in. So if your Event Bridge rule is able to successfully deliver the message to the Lambda service, which would be an asynchronous, I should bring that up, would be an asynchronous invocation, then the functionality of the retry and the retry policies of asynchronous Lambda function invocations are going to take over, and Event Bridge is now disconnected here. Another really cool thing that you can do, and this is one of the reasons why I really like to advocate for building single purpose functions, is because step functions are state machines that allow you to orchestrate workflows. This is something that Yen Trade put together. This is sort of this is a saga pattern where you book a hotel, book a flight, book a rental, and then if at any point along there one of those things gets canceled, the step function can actually go back and handle all of those different things that it has to do in order to orchestrate that workflow. So the Lambda functions themselves are all invoked synchronously, which means if they fail, there is no retry there. That actually gets kicked back up to the step function, and then you have a lot of control over how you want to retry it. So if there's a failure, there's a thing called catchers and retriers that you can put in all these complex patterns. You also get errors back. You get these sort of fancy error names back that you can do conditional error handling, which is pretty cool. And you can also set all your different retry policies. So things like, the back off rate and the max attempts and things like that. And then just the last part of this is AWS SDK. So I was under the false impression very early on that if you tried to make a call using the AWS SDK from a Lambda function, let's say you try to put something into an SQS queue, that if that failed, that you should try to retry that yourself. There actually are a number of automatic retries built into these, as well as the exponential backoff. So this is different depending on which SDK you're using, whether you're developing a Node or Java or Go or whatever. So it is specific to that AWS SDK. But for pretty much all of these things, if you try to make a call to an AWS service and that fails, the SDK will automatically retry for you. So if you're building in your own retries, you're just basically duplicating efforts that that likely they've built a better system for, that they've tested quite a few times. All right, so error handling patterns. This is the stuff that I like to talk about more than just sort of spitting documentation at you. Caching strategy is something that's super important. If we think about a typical AWS application or a serverless application where we're using API gateway, we're calling a Lambda function, and that Lambda function wants to query RDS. The problem is that RDS is going to be limited. It's not a serverless, even Aurora serverless is not really serverless. It's not going to scale up like you hope it would, not like DynamoDB or Lambda functions will. So if you get an influx of traffic here, it's very possible that for a read-heavy application, you could overwhelm not only just the RDS instance itself, but because of the way Lambda uses the connection model, the single concurrency model, you're most likely going to overwhelm your connections as well, unless you put something like RDS proxy in front of there. And again, still not going to scale for you, but it might handle those connections. So what we try to do is pretty simple solution. We just put a cache in front of this. If we get a hit from the cache, then we're going to go ahead and return that back to the customer. If we make a request and we call a cache, but we get a miss, we call RDS, we pull the data back. Elasticache is not a write-through cache, so we would have to manage actually writing that data back into Elasticache ourselves to make sure that that's updated, but then we would want to go ahead and write some data, and then return the data back to the client. So a couple key points here. We only want to connect to this RDS database when there's a miss. So if we have the same information being read over and over again and only a few outliers, then we can minimize the number of connections to our RDS cluster. We want to make sure we set appropriate TTLs so that we don't have the data last too long. We want it to expire at some point. And then we want to make sure we include the ability to invalidate the cache. So if we have another application writing to the RDS database, we should be managing that cache connection so that we can clear that out as well. If anybody is a computer science major, remembers their computer science classes where their professor told them that you should never put a cache in front of a database in order to mitigate the pressure on it. I totally agree. And what we want to make sure we do is still size that database appropriately. So if we're expecting to get 1,000 concurrent connections, we want to make sure that that database has more than 1,000 concurrent connections available to it or can handle that. This was nice when there are spikes and different things like that, because that way, even if it does exceed what our database capacity is, we hopefully can buffer that and give it a little bit of room to breathe. One of the things that is sort of new, that I don't typically talk about, but I think it's really interesting in this particular case with, especially in the case of, using RDS and Lambda functions, where there is some bit of a contention there, is the idea of using soft and hard timeouts for your data. So I would suggest always checking Elasticache for the data, right? Which is what you would do anyways. But then depending on what your hard timeout is versus your soft timeout, store two different values. So don't just expire data in Elasticache because it's been 5 minutes and now you want to go get new data. Maybe you set that to 2 hours with a soft timeout of 5 minutes. So if you go and you check Elasticache and the data is older than 5 minutes, then go check the database. And if you get data from the database, then you go ahead and finish that process. But if your database is down, is it okay to serve data that is 6 minutes old or 10 minutes old or whatever? So don't expire the data hoping that you'll be able to rehydrate it. Keep that data in the cache. Use those hard and soft timeouts so that you can determine whether or not, if the database call fails, you still have something to return to your customer. So another thing that we typically see with serverless applications is when you have write-heavy applications. So if we have data being written to an RDS cluster at a very high rate, it's possible for that to get overwhelmed. So instead, what we do is rather than write it directly, we put an SQSQ in front. This is something that Eric Johnson calls storage first, which I really like that idea. And essentially what we do is our Lambda function would make an asynchronous request to SQS. SQS would say, okay, hey, I got that message. And then we can immediately respond back to our client and say, we've got the data. And you can, this would be something like maybe for a webhook or anything like that, where you're going to have a maybe high throughput, or you could get bursts in data where you don't want to have to run your RDS cluster at, 3,000 connections when maybe you get a spike every, 5 hours or after a huge email goes out or something like that. So then what we would do is put another Lambda function in here where we would throttle it based off of the connection limits for our RDS cluster, limit that concurrency to match that throughput, and then we would poll the SQSQ. This would be synchronous, write the data to RDS, and then assuming everything went well, we just tell SQS, hey, we got the message, or we got the data, and they could clear out that batch. But if it was to fail, then this is where we could utilize that SQSQ, for example. In this particular situation, you couldn't use an event destination because one, you're technically invoking this Lambda function synchronously. Also, the failure is not at the function level, it's at the queue level. So when the data gets put back into the queue multiple times, that's when it would finally fail and go to SQS. So a couple key points here is that SQS adds a tremendous amount of durability. So as long as you can get to SQS, which is a very lightweight service, you don't have to worry about the scaling of that. Then the message has been captured and you don't have to worry about losing that. That throttled Lambda will reduce that downstream pressure, which is really great because, again, you don't want to oversize that database when you don't need to, but this is a good way to absorb those spikes. And then those failed events are going to get stored for further replay. The other thing you can do is actually get rid of this Lambda function. You can use what's called a service integration here, and you can actually write from API gateway directly to SQS. One of the things that we try to sort of preach, I guess, or I know that the AWS team preaches it as well, is you don't want to use Lambda functions for transportation. You want to use them for transformation. So this essentially would just be transporting data from API gateway to SQS. You can eliminate that, put it in there directly, and then if you needed to do a series of checks, maybe massage the data, format it a different way, whatever, you can do that in that throttled Lambda, and that would give you the control that you needed there. So another really popular pattern is called the circuit breaker. This is important if you are, say, calling a third-party API, for example. So let's say that we have a Lambda function that needs to call the Stripe API. In a perfect world, it calls a Stripe API that responds, and we go ahead and respond back to the client. But as we know from the beginning of this presentation, everything fails all the time. And it's very possible that there's a routing issue somewhere and we can't get to the API, or the API is overwhelmed. Maybe not the Stripe API, but certainly many other APIs are going to fail or going to be unavailable at some point. So rather than us just hammering those APIs saying, hey, why aren't you up yet? Why aren't you up yet? We want to be good citizens, and we want to figure out a way that we can minimize impact and reduce pressure on a service if it is starting to have performance problems. So the way that we do that is we actually add a status check, which would be in your Lambda function, but we add a status check in between every call. And what we would do is check some sort of a cache. So that could be DynamoDB, it could be Elasticache. And if the status of that says, hey, look, everything seems to be fine, then the circuit is closed, meaning that the electricity can flow through it. And we would send the request to the Stripe API. Now, assuming that this processes correctly and it responds back to us, that's great. We just respond back to the client, everything's great. But if we were to get a failure from that Stripe API, what we would do is we would increment that cache and we'd increment a failure count there, so that eventually, or I should say, so we would get a failure and we respond back to client saying, sorry, we can't make this connection now. And the client, by the way, doesn't necessarily have to be, somebody's laptop. It could be an SQSQ that's feeding it. It could be another service. It could be Kinesis. It could be all kinds of services that are feeding this. But essentially, we can respond back immediately to the client and say, okay, this failed. Once we get to a certain point with the number of let's say it's failed 100 times in the last 30 seconds, then we're going to flag the status check as open so that we won't even try calling the API. We're just going to say every request that comes in from this point forward, we're just going to tell them, sorry, we can't deal with it right now. But obviously we can't do that forever. So we do eventually have to check the API to see if it's up and running. And that's when we do what's called a half open status check. And we check to see if the Stripe API is now up and running. If it's not, that's fine. We just continue to fail like normal. But if it does succeed, then we want to update our cache and tell it, okay, hey, we're closed now, and we can go ahead and start sending traffic through. So a couple of key points with this. This is something that should almost be built into the services for you. It is not. So you do kind of have to build this yourself. There's different strategies for doing this. Important thing is to cache your cache with your warm function. So when a Lambda function executes, it'll usually stay active, meaning that if you call it again, it will unfreeze and any variables you saved will be there. So even if you had, say, 200 Lambda functions, concurrent Lambda functions that were hitting up against this API, you're not going to want to check the DynamoDB on every single call or Elasticache on every single call. So you can actually save some of that state. I mean, again, the idea is to mitigate as much as we can. It's not to be perfect. We just want to back off pressure. So if every Lambda function is even maintaining its own state, you might not even need to use a cache. You could do it that way. But if you did want to coordinate, you could use something like DynamoDB or Elasticache to help coordinate those things, but you don't want to check them every single time. You also want to use a reasonable failure count. I mean, this is one of those things where if you're sending 1,000 requests per second and it fails once, you don't want to stop sending requests. If you're sending 100 requests per second and you're getting a failure rate of 50%, well, then maybe that's enough to trigger it to stop sending messages because there's some issue there. Maybe it's latency based. Maybe you're expecting it to return within 1 second. If it goes over 1 second and that is for 50% of the requests, then you can flag that as open and stop sending traffic to it. And then again, going back to this, understanding item potency is an extremely important thing because clearly if the event fails, it could act, even though it might fail back to you, it might have successfully processed or taken time to process, or there was a timeout, or it didn't quite get back to you. So Stripe API, for example, has a very cool thing called item potency ID, where you just send in the same ID. That could be a hash of the message or the message ID or something like that that's the same for every repeated request that you send of the same type or the same message. Not every service has that, so just something to think about there as well. So the other cool thing we can do, another cool pattern, is this idea of conditional. I'm sorry, yeah?
Can I ask a question? Sorry, I put it in the chat, but
oh, I'm sorry. Yeah, I don't have that open.
That's okay. Actually, one slide back before circuit breaker.
Yep. Just get there. Sorry.
Right, yeah.
Too many animations on my slides.
Sorry, actually.
Here you go. Yeah.
Okay. Yeah. My question there is, I really like the model of the SQS to the Lambda protect the RDS, but what I'm wondering is there a middle ground? Because RDS doesn't scale super dynamically, even Aurora, as you said, but it does scale. And so I'm just wondering if you were getting, is there a middle ground where you'd allow a little pressure in so that the RDS, assuming it was Aurora, would scale up?
Right. Yeah, actually, that's a really good question. And so that's one of the things where I built a service called Serverless MySQL that is that basically will check the number of open connections and then kill zombie connections or even kill active connections in order to keep the percentage down to 70% or something like that. You can configure that. The problem is that if you do that with Aurora Serverless, then Aurora Serverless doesn't scale, right? So it's sort of like a catch-22 where it's like you want to put enough pressure on it so it does scale, but make sure that it doesn't scale too quickly, or it doesn't scale too slowly, I should say. So the reason why I like this SQS pattern, though, is and this is why I say you want to sort of size this RDS appropriately, based on the amount of data that you think you're going to be getting. Part of the reason for that is, again, if the throughput you expect is 1,000 requests per second or whatever it is, you want to size things so that it's going to be able to accept that. The reason why SQS is important is because RDS can go down for any number of reasons, right? So it might not just because it's overwhelmed. It could be anything. It goes into a maintenance window. Anything happens where it just becomes unavailable. You have outages and has to fail over to another availability zone, or you have to fail over to another region. So there's a number of reasons why RDS just could fail, and it has nothing to do with the pressure. And so putting SQS has local regionalized versions of it at every single availability zone in every region. And so it's always going to be there. And the likelihood of SQS failing versus the likelihood of RDS failing is very, very low. So RDS is a much higher failure rate than SQS is going to have. So typically what you're going to see is if your Lambda function is throttled, but maybe it's just throttled so it's, it only supports maybe, 500 active connections or something like that, those messages are going to flow through that queue very, very quickly. So you're not even going to really see a delay in it, but you're going to almost guarantee that message isn't going to get lost. So I get what you're saying is like, how do you then scale up that RDS cluster? And that's something where you could actually set like a CloudWatch alarm that says, if my SQS queue, if the number of messages in flight or the messages queued reaches a certain amount, then maybe I want to trigger some sort of auto scaling, right? Because that's the other thing you could do is even if you were using Aurora Serverless, you could set a Lambda function that responds to a CloudWatch alarm that then calls the API to trigger a scale up of Aurora Serverless. That to me, even though it's more complex and more complicated, I think it's a smarter architectural decision because you have that built-in failure and that built-in durability there that you're not going to get if you're just writing directly to the database.
I really like that, and I'll just say the use case I'm thinking of, both my current company and my last company, the load is very periodic. It's 9 to 5 lots, and then in the evening very little. So we want to scale it down at night, and then in the morning. To save money, but in the morning we don't want to be sitting on one instance. So anyway,
right.
I like the approach you suggested. Thanks.
No problem. All right, let me see if I can get through this. All right, so the other great service that has been introduced, it was introduced last year. It's been almost a year now, which is kind of crazy to think about, is Event Bridge. So one of the things that we can do here is, let's say we have a Lambda function that does some processing. So let's say a new order comes in, and every time a new order comes in, we want to run some sort of calculation and maybe send some data to Magento or to Salesforce or something like that. So it's sort of a disconnected thing. It doesn't need to be in our primary workflow. It's very low priority. It does need to get done. But what's great about using, oops, I went the wrong way. Great about using something like Event Bridge is now we can set a rule that says every time a new message comes into Event Bridge that says order received or order placed or whatever, those messages come in, we can use that rule to trigger that processing Lambda. Now, if that succeeds, we can do any number of things. We could send it back to Event Bridge as another thing to say, oh, Magento record added or Salesforce record updated or whatever that is. And then those can go off, and there's all kinds of other services that could process on that. Again, this might also update a database. It could do all kinds of things. If it fails, though, then there's a couple different cool things we can do by sending it to EventBridge as opposed to just sending it to an SQS. Again, sort of an advanced use case, but this could be really cool depending on what your workflow is. So we can set up a SQS DLQ for failed messages. But what we would do is we would use a rule in EventBridge to determine if it was a permanent failure. And that rule may look at the details. It may look at the stack trace. We may look for some data in there that says, oh, that was a 505 or a 404, or some other error where we said it's permanent. We're not going to be able to do anything with this, so let's just put it in this DLQ. But then there are other possibilities where it's like, oh, the Salesforce API just failed. It was just a we were over quota or something like that. Some error that could possibly be retried. Then we can actually add another route to the EventBridge system that says, what are the retriable failures? And if a bad message comes in, we can use that retry or that rule to put them into a different SQS queue that we're going to eventually replay. Now, maybe we don't want to replay it immediately. So there's a very cool feature in SQS called delivery delay, where we can actually delay a message's visibility for up to 15 minutes. So we could say, oh, maybe we'll set it to 5 minutes. We'll retry that message again in 5 minutes. Then you could have another Lambda function, and I know this is getting kind of complex, but it's really not, that is polling that replay SQS queue that doesn't see the message for 5 minutes or whatever it is because we use the delivery delay. That polls it, and then that actually invokes that processing Lambda asynchronously again, and then it goes ahead and it tries that. Now, you might want to use that replay Lambda to add some incremental count that says if that same message makes it back through here 4 times or whatever it is, then push it to the SQS. The cool thing about this is, even though it does seem a bit complex, is there are some really cool patterns that you could do where you could weed out those permanent failures from those replayable failures, and all of that could happen automatically for you. It would be 100% serverless, and you wouldn't have to be in there constantly inspecting it. You'd only have to go in and look at that SQS queue or the DLQ when something bad happened or when that started to back up. So the last thing I want to talk about is decoupling our services. So SNS has always been sort of the pub sub service of serverless applications. And again, this is that idea where you send that asynchronous request to it, you get the message back, the client disconnects, and then SNS is now responsible for distributing that to whatever subscriptions it has. And essentially, it works almost as like its own little event service. And before EventBridge existed, I used to use SNS essentially as a messaging bus, where I would have it live as its own service. I would publish to that with, of course, a well-defined API. And then I could use that to send messages to SQS or HTTP or to Lambda functions and things like that. And then now they've added the ability for, if those things fail, you can actually write them to the DLQ. SNS is a very well-defined API. If you're thinking about microservices, even though there's no good definition of it, one of the things we like to say with microservices, they should have a well-defined API. Well, SNS isn't going to change. So if you have one SNS service that is used by multiple services, that's kind of okay because you know that API is not going to change. This does decouple those downstream processes, right? So that means that I don't have to wait for, I don't have to individually invoke a Lambda function or individually invoke SQS or send an email or any of those things. I can do that all asynchronously simply by delegating all of that to SNS, and then all those failures can be handled there, and I don't have to worry about my client waiting too long for those things to be processed. And because you can add message filters, you can actually have multiple subscribers where only certain rules get triggered, again, similar to the EventBridge rules, where only certain things get triggered, depending on what the message content is. Those are kind of a pain, though, because you have to look at special message attributes and whatever. So now that EventBridge is here, this is sort of my de facto event bus for pretty much everything that I've been building. And essentially, it's the same thing. The client calls Amazon EventBridge. It's an asynchronous request. You actually get an event ID back with this, which is kind of cool because if you did want to do some tracing or tracking, you'd be able to see what happened to that particular event. And this has the same features for the most part as SNS, where you can call SQSQ or Lambda. But what's really cool about this is you can call step functions. So you can't invoke a step function using SNS. The only way to invoke a step function before was to actually have a Lambda function that then invoked the step function itself. Now, every time you add a new piece of a new Lego block here. Now you've added a Lambda function that has to run. That Lambda function then has to make the SDK call, and the step function has to kick off. There's so many failures in there that are possible that you might never kick off that step function. You'd have to manage that whole failure path and the retry path. Whereas with the Amazon Event Bridge, you simply set up a rule, and it's going to try to invoke that step function for 24 hours until it says, yes, I was invoked. You can also send messages to other event buses. And then there's 16 other downstream targets that you can send it to, which is pretty cool. You have the message filters on all of these as well. So again, you can have, I think it's up to, I want to say up to 400 rules per target or something crazy like that. So there's a lot of things that you can do here, and you can be very prescriptive about which things get triggered off of the messages coming through EventBridge. So a couple key points here is multiple subscribers. They have complex rules and patterns. This is something that reads the JSON of the event directly, whereas SNS, you have to look at special message parameters that are part of that. This just looks at the data that is coming through. So you can build all kinds of complex rules and decide what gets sent and what invokes different things under what conditions. You can forward them to other accounts. So if you are separating your accounts, maybe some microservices are separated across multiple accounts, you can forward messages back and forth. And then again, we talked about that 24 hours of automated retries. And so where this would come in an application itself is if we looked at that standard sort of API gateway call to a Lambda function, we would write, let's say it's an order gets placed. We write to the EventBridge bus that an order was placed, and then we get that ACK back. We respond back to our client and said, okay, great, we've received your order. I'm sure you've noticed if you've ever placed an order on Amazon.com or Dell or any of these sites, it'll say, all right, we've got your order. And then you get an email a few minutes later or a few seconds later. All of that is happening asynchronously behind the scenes, right? We're not waiting for it to charge your credit card and do all this other work directly. That's all being delegated to asynchronous processes. So once that message is written to EventBridge, what's really cool is now we can have all these other services that are completely disconnected, completely independent. The API Gateway Lambda order process or order submission process knows nothing about these other services, nor do they need to. But what we do is we subscribe this order service, this SQSQ that would be within this order service. We add a rule and we subscribe to the EventBridge, and we say anytime we get that order completed, we want to go ahead, or order sent, we want to go ahead and put it in the SQSQ, pull it with a Lambda function, write it to RDS, and then tell SQS that we've got it. Now that process is done, and you could trigger some other event off of that if you wanted to. But what's great is now somebody comes along and says, well, wait a minute, we actually have to alert these people with SMS. So another team or the same team or whatever could build another service that neither the order service knows about or the order submission process knows about that adds another rule. And they subscribe to that. It writes the data to the SQSQ. It calls the Twilio API with a Lambda function and does all the work there. And then maybe we want to have a billing service that runs the rules and bills the credit card, does that same thing there. So these four independent services know nothing about one another other than there's going to be an event that comes and that they've got some requirements that need to do. So what's cool about these rules is you could say, okay, we only want to trigger this particular SQSQ when the detail type is order complete. And that's just a simple rule that says, okay, great, this is the order or the event type. But maybe you want to do something more complex where you say, well, we only want to trigger the billing service if the value is greater than 0. So maybe we offer, some free ebook that you can buy and you still go through the process and give us your information, but we don't want to bill your credit card, for example. So what's cool about this is that you can filter these events very selectively or selectively trigger all these different services based off of these rules. And these rules can get very complex. They're 100% infrastructure as code, right? So they're very easy to check in, have a Git flow around and all that kind of stuff to make sure that they are done correctly. Each one of these individual services now, we're not trying to call our alerting service, our order service, and our billing service synchronously from our Lambda function. We've disconnected it, which means that each one of these services can be have their own failure modes, their own throttling done, whatever quotas there might be. Maybe we get a big influx of messages, but we've got a quota for Twilio where we can only send 100 or 1,000 messages an hour. We could manage that quota inside that SMS alerting service. The rest of the system doesn't need to know anything about that. And then in the case of Lambda destinations, if you are triggering anything asynchronously, like if you were triggering a Lambda function asynchronously, you would want to use Lambda destination just because it's, again, it's a better way to do it. All right, so a couple key takeaways: just be prepared for failure because everything fails all the time, and don't blame yourself if something's failing. Just be prepared for it. You want to make sure you utilize those built-in retry mechanisms of the cloud, right? They're there for you. Again, the cloud is much better than all of us when it comes to the number of times they've tested these retry policies and everything that they do. So it's just a matter of letting them actually handling that. In order to do that, you do have to understand these different failure modes. There's a ton of them. There's a ton of different ways that these messages can be dealt with, but just know that they are different, and go in and study them when you come across using a different way to invoke a Lambda function or a different service that you're using. Again, buffer and throttle events to distributed systems. And finally, just embrace this asynchronous process to decouple components. Not everything has to happen immediately, because it is, you don't need to get that order confirmation email, within 1 second of placing the order. If you get it a minute later, that's probably fine. And there's plenty of other things like syncing data into Salesforce and some of those other things that certainly can happen after the fact. Copying data for analytics and some of those other things. Those are all easily asynchronous processes that can be run, and you don't have to worry about overwhelming systems. And you can, again, be very, very prescriptive about how each one of those services handles it, and what the throughput is on each of those. So that's basically it. Some information about me and some things that I'm working on. And thank you very much for having me.
Awesome. Wow. Thank you very much. That was fantastic. I will open the floor to anybody that has any questions or wants to. This is not Stump the Chump. So.
Yeah, really.
You can try.
One of the topics I'm curious to hear a little bit more about, when you were talking about SQS, one of the key points you made was that it's at least once. And for a lot of people, that can deter them thinking that they have to write some sort of logic to make sure they're only processing records once. I know with FIFO queues, you have the ability to guarantee only once delivery. What are your thoughts on that? Is that a pattern you recommend, or would you recommend the developer takes that ownership and writes it in the code?
I think it depends on what you're trying to build and what your use case is. So what I really like about FIFO queues, so it used to be with FIFO queues, you couldn't actually attach a Lambda function to them. You couldn't subscribe to them. That changed, I think it was last year. And the thing that's very cool about the FIFO queues is you can now use the message group ID, which essentially works as the shard ID. So if you do have a need for guaranteed order processing and things like that, then certainly FIFO queues are really great. And like what I have used them for now is if I have multiple client streams that are being processed, like a client is submitting something, then I can say, oh, this is client 1, this is client 2, this is client 3. I can break those up into separate message group IDs so that I can process those. And then that way I know, because I don't have to worry about, as long as the client, per client, it's in order, that's all I care about, right? But if you are doing batches of 10, even with FIFO queues, it is possible for those to fail and put those messages back into the queue, and then you would be reprocessing potentially the same messages over again. So there's a couple different ways to think about where the idempotent operation is. So there's an idempotent operation, which is getting the message out of the queue. I get a unique message ID. And that unique message ID I could use as an idempotency key for whatever downstream service. So I could say, if I'm inserting something into a database as a result of pulling something from a queue, I could use that message ID to say, okay, I want to make sure that that if this message ID already exists, I'm not rewriting that data. So that's one strategy you could use. And you can use that on both. So you can use that with FIFO queues or just the regular SQS queues. That's one place where you can be pretty sure that you're handling idempotency okay. The bigger problem comes if the same event is submitted multiple times into the SQS queue. So that is a different way in which you can get duplicate events. And that is probably more likely, well, I shouldn't say that. It's easier to use that message ID so that you can make sure you don't insert it multiple times into whatever the downstream is. But if you do get the same event, the other option is to take a part of the message itself and just create a hash, some sort of fingerprint out of that, and use that to know whether or not you've gotten the same event more than once, and mitigate it that way. So So yeah, I don't think you get anything in terms of item potency protection from from FIFO queues versus the other queues. I think either way, you're still going to have to manage it either on the front end, on the back end, or both.
Okay, cool. Thank you for that answer.
One thing that struck me, I'll say from one of your very first slides when you're talking about the monolith, there's the monolith, then the single function, then the middle one, the whole application, and that most of the lambdas I write are for Alexa, and those are all in that middle category where I've got one lambda that has to handle anything my Alexa skill does, and it's just interesting to have a it's interesting to have a name for that.
Yeah, well, so I mean I don't know if I think people agree on the lambda lith. That's the the monolithic lambda function, or the mono lambda is something that sometimes people call it. And then clearly the single purpose function I think is pretty straightforward. That one in the middle, that I call it the fat lambda because I don't think it's a bad pattern. I think there are plenty of reasons why, for efficiency standpoint, especially from a distributed system standpoint, you do not want to have to connect or have to be communicating between 5 different functions in order to accomplish something that is going to happen synchronously or is going to happen within the same request. So rather than splitting that out, taking that data and putting it all together, or taking those I guess subroutines and putting them all into one function makes a ton of sense there. The Lambda team, and certainly the dev advocates for serverless at AWS, argue very much so that, hey, we should be doing single purpose Lambda functions. And I agree with them. But then you get other teams like the Alexa team who, that's really the only way to do it, is to just build a big fat Lambda that handles all these different things. So the messaging isn't always clear, but that's why I don't like to criticize the fat Lambda, because I think there are plenty of reasons why you need it, why it makes sense. And why it is actually better in some circumstances than breaking things up into multiple Lambda functions.
Yeah, I think I've heard of some Alexa folks talking about having a main Lambda that then farms off each of its intents to other Lambdas, and that just seems wrong to me.
No, Lambdas calling Lambdas is a dangerous game.
They want you to pay twice, Brian. That's the trick.
That's right. You not only pay twice, you pay while the first Lambda is waiting too.
Yeah, exactly. So one of the things when you were talking about the total failures and talking about the different approaches, one of the benefits that I think is so great about the single purpose, or some of the benefits you might get with the FAT, is when you do the total failure, you trigger the AWS CloudWatch metric for Lambda failures. And so It's really easy to create alarms and alerts, and third-party systems can look at those metrics really well too. So one of the biggest benefits, I think, from that approach is the ability to trigger those AWS metrics and have your alerting and monitoring based on them. So one of the big takeaways I take from that.
Yeah, I actually didn't mention that. That's a really good point. And I did mention that, again, when you get failures, you can use CloudWatch alarms to track things like when there's too many messages in the database, for example. Too many messages in like an SQS queue. But that's a really good point. And anytime you trigger the failure modes of the cloud, you get all the benefits of what that is. So the ability for you to say, okay, now I've had X number of failures in this Lambda function or whatever it is, those metrics are very useful. And like you said, yeah, because swallowing errors, I see it all the time. People just swallow errors, and then they have to look through CloudWatch logs in order to figure out that there was an error because they logged the error there. But then New Relic or Thundra or any of those things can't actually pick up the fact that it was an error because it wasn't flagged as an error, in the AWS system.
One quick thing, I know people are asking questions. Maybe Chris, you were about to say it, but I dropped the link for the survey. So please, folks, if you were able to join by filling out this survey, you are entered into a raffle to win $25 AWS credits. So that you can spin up all of your RDS instances and have all of your dead letter queues misconfigured and pay for 10 billion Lambda requests. We'll cover you for $25 worth of that if you fill out the survey and win the raffle. So please fill that out if you get a chance.
Cool. How many responses do we have now, Mr. Planky?
2. whopping 2. So your chances of winning right now are pretty high. If you're one of the 2 that entered, it's 100%.
50%.
Yeah.
Well, seeing as how one of them is mine, the other person has a 100% chance of winning.
Wow.
All right, so get in the survey. If you can, at the bottom of it, there's also a section for what you want to hear, what you the things that you want to have us line up for you for the next events. And we need that information so that we can make sure that we get the right kinds of people, just like Mr. Daly. Jeremy, now that I've said your name 17 times as Daly, how do you pronounce your last name?
Daily.
Thank you. Okay, I was like,
There you go.
I was like, does he say Daly? I hope not.
No. It's Irish. It's just Daily.
Cool.
Straight Daily.
All right, I'm gonna go ahead and stop recording now because